This is where we left off on resonance. Suppose you have a pendulum, which you might have learned in physics. If you have a load on a string and you throw away this string this way, so the string will come this way with the load, but it's gonna swing over onto the other side. That's like an example of a resonance. So same thing applies with electrons on a Lewis structure. They can be moved around the structure using arrows, but you don't rotate the structure. You don't lose the number of atoms of the elements on the structure. It's just switching position of charges and the bonds. So if you do that, you get more than one correct Lewis structures, of which these structures are equivalent. They're just having bonds and electrons on different positions. The assumption in this diagram is that the atom position do not change, like I said. We are only allowed to change the distribution of electrons or the position of electrons, thus the bonds and the lone pairs. Now, the Lewis structures don't explain properties of molecules. In fact, they don't even explain the shapes. Resonance theory is just a second reasoning that will help you to understand shapes. Now, let's say you need to draw the Lewis structure of NO3. Just to remind you, start by calculating the total number of valency. This is for nitrogen, this is for the 3 oxygens. Each oxygen has a valency of 6, is in main group 6. Nitrogen is main group 5. And then you have a negative charge, so you add 1. This will be the total valent electrons. And then you would look for symmetry, and then you'll make at least a bond. And then oxygen is furthest to the right than nitrogen, so you satisfy its octet. So far we've used 24 electrons, but nitrogen is still not happy, so you would donate 2 electrons from either of the 3 oxygens, and then at least make a bond. So you'll realize that you'll be left with this structure. And then you calculate your formal charges. You'll find that these 2 oxygen will have a formal charge of minus, like we did in the last class. The nitrogen will have a formal charge of plus. Do that calculation. Formal charge equals to number of electrons, number of valence electrons on neutral atom, just like it's found on the periodic table, minus non-bonding electrons, minus number of bonds, So apply that formula, you'll find that you have a negative here, you'll have a negative here, and you'll have a positive there. Okay, so this is just one of the structures of what we call a nitrate. Can we make more structures out of this valid Lewis structure? The answer is yes. So depending on your choice of the diol bond to oxygen, there are 3 possible structures. So what you'll do, just to refresh your mind, you would use a double-ended arrow to move 2 electrons. So remember, 1 electron was moved by a fishhook. So here we want to move and open up a pi bond. So I should start where the negative charge is. In fact, in resonance, the shortcut is start at negative charge point or negatively charged atom of an element, or element, whatever you would call it, and negatively charged element, let's say, so because oxygen is an element, and in the element you have the atom. Start at the negative charge element. Alternatively, if there's no negative charges, you want to start at the pi bond. So this is only when there's no negatively charged element. And also you push push electrons towards positive side, either partially positive or fully positive side of the structure. So in this case, this one here is the positively charged element, so I can start either from here, and you realize if I do that and if I don't open up this pi bond, then there's gonna be more than 8 electrons on that nitrogen, because you're moving these 2 electrons in between, you're making a second bond, you're left with 2 lone pairs. This oxygen down here is not touched. That one is still having its 6 electrons. So you see you have 1, 2, 3, 4, 5 bonds. Each bond is 2 electrons, so you have 10 electrons around the nitrogen. That's not valid. That's why once you push here, you have to push that one on the other side. Notice that nitrogen has maintained its 4 bonds, so it's still going to have its positive formal charge. You have to do the math, the formal charge calculations after each resonance. So this opened up towards the oxygen. Now oxygen has 8 electrons around itself. Okay, so it has 8 electrons around itself. So if you do your calculation, the answer here is gonna be negative. The reason being, one of the shared electron belongs to nitrogen, one belongs to oxygen. You know, oxygen legally has a valency of 6, but now it has a valency of 7, including this one that was shared, the 6 black ones and this one. So it's 7. 6 minus 7, shortcut gives you -1. Same applies to these guys. Now nitrogen, if you are to consider nitrogen using this shortcut, you have 4 bonds, which means that this nitrogen right here is donating 4 electrons to make the 4 bonds. The oxygen will bring the next one. This oxygen down here will bring the other 2, and this oxygen here will bring 1 more. So basically these are the electrons belonging to nitrogen, the ones I'm boxing up. But nitrogen legally has a valency of 5. So again we'll say 5 minus 4, that is using here to share, donating here to share, gives you +1, and so forth and so forth. Now let's draw the next resonance structure. You see the pi bond was here, it's now down here after the resonance. So we do it again. This time I'm gonna use the this lone pair to make a double bond, and again I have to open this up to avoid the 10 electrons around nitrogen. You end up with this structure. So you made a double bond to your right. This down oxygen, the bottom oxygen now has 6 electrons. Calculate your formal charge the way we did here, or use your formula that we mentioned here. You'll find that these 2 oxygens will have negative charges. The nitrogen will have a positive charge. So again, you will have moved the pi bond from here to the top right. So you see we are moving electrons around, in turn you're moving charges around. That's what's called resonance. Okay, we are not rotating the molecule. Nope, we are not rotating the molecule on the plane. We are just pushing arrows to make new structures with different location of the double bond and charges. So what if you're given NO2? So probably, if you are to draw the structure of NO2, probably you will have, let me see which will be the most valid here. There are rules for valid Lewis structures. First, you want to minimize charges. Of course, you have to maximize octet rule for elements that can have 8 electrons around them, except helium and hydrogen. And then, of course, you want to you want the positive charge on less electronegative element, which means you want the negative charge on more electronegative element because it wants those electrons. These are the common rules for finding the best Lewis structure. Now, so in this case, this would be the best right here, because you will have the negative charge on oxygen rather than negative charge on nitrogen. This one does not obey octet rules, so it's not it's not valid. This is invalid. This is valid, but the charges are misplaced, so it's not the best. This is gonna be the best Lewis structure because it's obeying all this. Everything is octet. All elements are octet. They have 8 electrons around them. We've maximized the octet rule. We'll minimize charges here because plus and negative will cancel, and the positive charge is on the less electronegative element, which is nitrogen, which is to the left of oxygen on the periodic table. Electronegativity increases across the periodic table like that. So negative charge on more electronegative, which is oxygen, so which is here. So the negative charge is right there. So this was gonna be the best. Anyway, we are talking about resonance. So I'll push again from the negative charged element towards the plus sign. In between the two elements, I make a pi bond, but I don't want to leave it there, because if I leave it there, then the nitrogen is gonna have 10 electrons, 6 this side. Each bond is 2 electrons for this side. That's not good. So we have to open up. As we push up, making a bond here, we have to open this towards the nitrogen. Okay, so if you do that pushing, you're gonna end up with this structure right there. The resonance structure is denoted by a double arrow like this. Okay, now if you want to get this structure right here, let me see how we'll get that. You would push this one here and push this one here, and that's a wrong arrow pushing, because you don't want to push electrons where there's a negative charge. Like charges repel. That's why I told you this is invalid. This one here is invalid. I wouldn't even care showing it. It's so wrong, because you really want to push electrons towards the positive side. This is a negative side, so that's invalid. Okay, and also you don't want to steal electrons from a positive center. So this one here would have been formed if we did this, and I put excess there because this is invalid. It should not be formed. These are the only two guys that I would expect to be shown as Lewis structure. This will be the valid, this will be the best, because it follows all these rules. Okay, so now let's talk about molecular geometry. Shapes of molecules. Molecular shapes. So to find the shapes of molecules, all you're doing is you are describing the position of the atoms relative to one another. So for example, if this is black, as we see, we usually use black ball for carbon, and we use the white one for hydrogen. So probably this is a best representation of this structure right here. Okay, and that is a methane. But it's not the only one that will take that shape. It's just one of the examples. So you see, this looks, if you connect the atoms, okay, if you connect the atoms, you get a tetrahedral shape. So this is what you're gearing to describe. So this is tetrahedral. Molecular shape, molecular geometry, Mg, tetrahedral. with one of the atoms right in the middle of the structure. So that's tetrahedral. You are connecting atoms. I'll repeat. For molecular geometry, you're connecting atoms in the shape. For electronic geometry, we will be considering the bonds and lone pairs. So here is an example. Here are other examples. So if you are to consider elements A and B combined to make a molecule, where N is a number of B's available, A most likely is going to be the central element. So let's say for this one, AB2, N is 2, because those are the outer atoms. That's an atom, It happens to be red. For red, that should be oxygen. This should be oxygen. Okay, those are 2 oxygens. So, and I see a double bond, so this should be your A, and this should be your B, that should be your B. That's where I get AB2. So actually, this is black, so that should be a carbon. So the representation here is that one of carbon dioxide. So again, I'm not considering the bonds, I'm considering connectivity of the atoms for molecular shape. It's a straight line, so it has to be linear. Okay, so this one is of the general representation AB3. It so happens that you're gonna get, okay, the bond angle here is 180 degrees, I forgot to mention this. It so happens that for this system, you're going to get 120, 120, 120. Obviously, 120 times 3 gives you a circle, which is 360 degrees. Here, the elements are well spread. There's maximum accountability of space. So it's not less than 120 or greater than 120, it's just 120. Now, the best example I'll give you for AB3 is usually formaldehyde. Okay, disregard the colors for now. So this will be 120, 120, and 120 degrees. I already talked about tetrahedral, and the best example I'll give you is where 2 hydrogens are on the plane of your monitor, and then one hydrogen will be to the back, the other one will be towards you, pointing outwards from your screen. This is pointing, this guy is at the back of your screen, this is popping out of your screen, and these 2 are on the plane as your screen. So the bond angle is not 90. Lewis failed because all Lewis did was to draw it like this. This would assume that this bond angle is 90, but hey, you know what's inside the bonds? The electrons, and the electrons are negatively charged. Like charges kept close together will repel. So that repulsion causes the bond to be greater than 90, and in actual sense, it's approximately 109.5. The bond angle is approximately 109.5 degrees for tetrahedral. So for all tetrahedrals, the bond angle is 109.5 approximately. Of course, now if you are to find the formula for this, it would have been AB4. We started with A, B2, AB3, AB4. There's another one for AB, which will be an example of what you have in carbon monoxide. Is still going to be linear. Of course, the bond angle is still going to be 180 degrees, just like in AB2. Here, I think you have 1, 2, 3, 4, 5. So you have A, B, 5. The A will be the center point, the atom in the middle, and then the greens are outside. As an example, I'll give you PCl5. Phosphorus is one of those elements that can take more than an octet and just still be happy. So this is just an example I'm giving you of an inorganic compound. So the bond angle here is 90, but the bond angle here is 120. There's a mixture of bond angle. So where you have a mixture of 90 and 120 degrees, that's trigonal bipyramidal, because on top you're making a pyramid. Okay, this should be away, this should be towards, that should be on the plane. On the top you're making a pyramid. If you connect these elements, they give you a pyramid, like the pyramids in Egypt. At the bottom you still have the same pyramid. If you are to connect them, you get another pyramid. So it's bipyramid. It's trigonal because the base of the pyramid is 3 atoms, or 3 connections, 3 vertices. Okay, here you have octahedral, which will take the general formula AB6. The bond angle all over the place is gonna be 90 degrees, whichever way you look at it. So those are molecular shapes considering connectivity of atoms. Okay, so when n is 2, for example, you can also get it. Okay, so let me see. When n is 2, you can get it as bent, or you can get it as linear. For example, in CO2, we said it's gonna be straight line. This is A, that's B, that's B. But in water, it's gonna be bent, because these 2 lone pairs on the Lewis structure of water will occupy much volume, and like I said, electrons repel. According to valence shell electron pair repulsion theory, which is coming up, they repel. So that forces this hydrogen, instead of them being on a straight line with the oxygen, the lone pairs will push this down and push this bond down, because the lone pairs occupy much volume on top. So you get a bending effect. So overall, if you are to connect the atoms, because that's how you get molecular shape, you simply connect the atoms, it's bent. Okay, another example of a bent Lewis structure is that one of sulfur dioxide, which will also be bent. Okay, why? Because there's a presence of a lone pair on the sulfur to make it octet, which forces the bonds downwards, because it's like having a big balloon here and smaller balloons representing the bonds. The big balloon will push the small balloons down and makes the molecular shape bent. Of course, I've talked about trigonal pyramidal. Square pyramidal is where you'll have, okay, when n is 4, you either get it as square, planar, seesaw, or tetrahedral. It's not shown here. So where you have 4 groups attached to the central atom, 4 equal elements attached to the central atom, you're gonna get all these 5 elements on the plane sitting flat on your desk. Then it's a square if you connect the outer elements, and it's on the plane, so it's square planar. Seesaw is where you have a central element, alright, and it's gonna be connected to 4 others. So it's like a seesaw where one person would sit here, okay, and the other person will sit here. Excuse my drawing. And then you'll be swinging, and this would have been the support, like in the playground. So this would be seesaw representation. The seesaw shape and the square planar are not common. In fact, even T-shape are not common in organic chemistry, so I'll not talk about those. Okay, I've talked about square. Did I talk about square pyramidal? Let me see, I didn't. So square pyramidal is where you have 5 elements connected to a central one, and one of them is on top. So you get a square pyramidal because the base has 4 B's, and then it's 3D. One of the B's is on top. The 5th B is on top. That's why you get 5. You have 5 B's. Again, this is not common in organic chemistry. This is not common in organic chemistry. This is not common in our organic chemistry. This is not common in our organic chemistry. The one that's common in organic chemistry is going to be bent linear trigonal pyramidal, trigonal planar, tetrahedral. Those are the ones which are common. So I keep saying that water is not linear. I keep saying that H2O shape is not linear. It's bent. It's bent. Like I said again, the lone pairs will occupy much volume on the oxygen than the 2 electrons making these 2 bonds. So that causes a repulsion because electrons are negatively charged. Like charges repel. So the electrons that make the bond will be repelled further down by the big cloud of lone pairs. Okay, these are repelled further down. So that's how you get the bent shape rather than having it linear. So the theory that explains it is called valence shell electron pair. Electron pair, electron pair. The electron pairs are causing repulsion. Valence shell electron pair repulsion theory. So instead of having 180 degrees bond angle, actually you're gonna get 109.5 degrees. The angle will decrease between the two bonds. The bond angle will decrease because of the 2 lone pairs that repels the bond and forces the bonds to come towards each other. Based on valence shell electron pair repulsion theory, which helps to explain the molecular shape. The theory uses the concept that like charges repel. Of course, these are the electrons. To explain how geometry are brought by, I explained, for example, water is not linear, it's bent. For example, water is not linear, it's bent. Okay, so the electron pairs occupy much volume and they repel these bonds further away, decreasing the bond angle from what would have been 180 to 109.5, and one would expect the electronic geometry to be tetrahedral, but the molecular geometry will be bent. Each time you have a lone pair on the central atom, the electronic geometry, which is about to be described, will be different from the molecular geometry. Okay, let's see. Actually, do we have it here? You have it there. Okay, so we need to know the number of electron pairs, assuming you know how to draw the Lewis structures, to explain valence shell electron pair theory. So determine the number of non-bonding electron pairs, single bonds, double bonds, triple bonds. So in fact, I'm gonna call these electron domains. So what is an electron domain? An electron domain is one that has a lone pair. So one lone pair is an electron domain. So a lone pair is an electron domain. I know there are 2 electrons, but that's one electron domain. Single bond, it's 1 electron domain. Double bond, yes, it says double, but it's gonna be taken as 1 cloud, 1 electron domain. Okay, I don't know why I wrote that. I needed to write double bond. So all these are 1 electron domains. Lone pairs are 1 electron domain. Single bonds are single electron domain. Double bond is a 1 electron domain. Triple bond is a 1 electron domain. It says triple, but that's 1 electron domain because the 6 electrons that make the triple bond are in 1 balloon, 1 cloud, 1 hybridized orbital. Okay. So now, electron domains help to give you electronic geometry, and that's found by looking at the arrangement of bonds and non-bonding electron pairs around the central atom. In contrast, molecular geometry is the arrangement of the atoms. Be very clear. For example, H2O. We say the molecular geometry is bent because we are just connecting the atoms. But is it the same as electron geometry? The answer is no. How many electron domains do we have? I have a bond, so that's one electron domain. This is another one, a lone pair is an electron domain, that's another one, and that's another one. So I have 4 electron domains. So if you have 4 electron domains, the bonds and the 2 lone pairs, so this will be the bonds, not 2 lone pairs. Then you have 4 electron domains. If you have 4 electron domains, the electronic geometry is tetrahedral. So I told you, whenever you have a lone pair on the central atom, always consider the central atom for the electronic shape. Whenever you have at least a lone pair on the central atom, the Mg, molecular geometry, will always be different from the Eg, electronic geometry. This distinction is very, very important. But now let's look at an example of methane. Okay. How many electronic domains around the central atom? Of course, there are 4 bonds, so 4 electron domains. So I expect that the electronic shape should be tetrahedral because I'm talking about electrons, electron domain, so I'm looking at electronic geometry. Now for molecular geometry, I consider the atoms. I simply connect the atoms, and that tends to give me a tetrahedral shape still. Notice that in this case, the molecular geometry Mg is the same as the electronic geometry Eg. Why? Because there is no lone pair on central atom. There is no lone pair on the central atom. So Eg is the same as Mg. Compared to H2O, you have at least a lone pair, so Mg is expected to be different from Eg. It's bent, connecting the atoms. It looks like an inverted B for Mg, molecular geometry, but here I do have a bond, and 2 lone pairs, 4 electron domains. It has to be tetrahedral. So bent molecular geometry, tetrahedral electronic geometry. Here they are both tetrahedral. The Eg and Mg is the same. Okay, continuing with valence shell electron pair repulsion theory. For carbons, we are limited to 4 groups around the central atom. That's the maximum you can go. You can go 4, 3, 2, or 1. For example, carbon monoxide. So you would see that if you are considering, let's see, what are we considering? If you are considering the Eg, okay, so let's say you have carbon dioxide, sorry. Again, we focus on the central atom. So if you're considering the carbon dioxide electronic geometry, I have a double bond. Again, you're considering what's connected on the central atom, not further away. I'm not caring about these lone pairs on oxygen. So what's connected on the central atom? How many electron domains around the central atom? So I have a double bond. That's 1 electron domain. Remember the rule we said that electron domains are 1 lone pair, 1 single bond, a double bond, a triple bond. Those are single electron domains. So I have 1 electronic domain here, and then I have another electronic domain here. So total, I have 2 electron domains. So obviously, if you have 2 electron domains and they're on the same line, then it has to be linear. That's what represented down here. This is linear electronic domain. Do we have a lone pair on the central atom? We don't have a lone pair. So I expect the Mg to be the same as Eg, and it has to be linear. Remember, molecular geometry, you're connecting the atoms O, C, O. They're on the straight line, so it's linear. So what about trigonal planar? Considering this molecule, I don't have a lone pair on the central atom, so Eg must be equal to mg. Electronic geometry is the same as electronic molecular geometry. And let's look at electronic geometry. How many domains, electronic domains, do I have? I have a single bond, and a double bond. So I have 3 electron domains. If I have 3 electron domains, I would expect the bond angle to be 120, because 360 again divided by 3 is 120. I don't expect any much repulsion. The bonds will repel each other. Lewis would say that this would have been the shape, but that would have been wrong, because you want to maximize the space between bonds, because those are electrons which will repel each other according to valence shell electron pair repulsion theory. So the hydrogen will be pushed further down. This hydrogen will be pushed further down, and so this is not the correct position, and that's why it's drawn that way. And the bond angle in between will be roughly 120. Anyway, you have 3 electron domains. That should be trigonal planar. Mg, trigonal planar. They're the same because there's no lone pair on the central atom. I talked about what is going to be bent for Mg, but you have 4 electron domains around the oxygen, so Eg would be tetrahedral. Okay, this one I've already mentioned it. Eg and Mg is tetrahedral. You have 4 electron domains. Eg is tetrahedral. There's no lone pair on central atom. Molecular geometry will be the same tetrahedral. Here, the electronic geometry will be tetrahedral. Why? I have a lone pair. I have a bond, and a bond. Those are 4 electron domains, which always gives you tetrahedral. Bond angle will be 109.5. I'll keep telling you that for tetrahedral, the bond angle will always be 109.5. But the molecular geometry will be different. Why? Because we at least have a lone pair on the central atom. Eg must be different from Mg. Molecular geometry is found by connecting the atoms, so I disregard the lone pair. I focus on the atoms. I have hydrogens, 3 hydrogens and nitrogen. Connect these guys, you're gonna get a pyramid. The base has 3 atoms, so it's trigonal, but it's a pyramid. So we'll talk next about hybridization when we meet on Monday virtually. This covers Thursday, June 4th lectures.